Hello everyone, my name is Charles Zenal, and today I'm going to be talking to you guys about open channel flow, and at the end of this discussion I'll be answering some of the questions you guys had for me. During this discussion I'll be talking about the S1 and S2 profile. The S2 profile is on the left side and is denoted by the sloping downward portion. The S1 profile is on the right side and is denoted by the upwards curving portion. S0 additionally is the slope at which the entire channel is at. So this is the results from the experiment for the S1 profile. As you can see, as the X location increases, so does the Y, which follows closely with the diagram I showed you earlier. Next, we were able to find the theoretical data for the S1 profile using a multitude of equations. We found the X position, the Y depth, and some other variables such as the Freud number, the slope, and the dy dx. And in the next slide, we're going to compare the graph of the theoretical data and the experimental data. This is the graph of the experimental and theoretical data for the S1 profile. The experimental data is denoted with the dots and the theoretical data is shown with the line. And as you can see, there's a strong correlation between the two, meaning that the data we collected in the laboratory was very accurate because we know the theoretical data is correct. Moving on to the S2 profile, we can see from this data that as the X increases, we have a decreasing Y up into a point where it becomes constant. And this does agree with what we saw in the first chart I showed you, where we had the decreasing slope. Similar to the S1 profile, we were able to calculate the theoretical data for the S2 profile, and as you can see, it does follow similar to what we found from the experimental data. This is the chart representing the experimental and theoretical data for the S2 profile. The line represents the theoretical data, and the points represent the experimental data, similar to before. As you can see, there's a few of the points that are not exactly on the line, and those are going to be due to some experimental errors, maybe in the height measurement or the position along the x-axis measurement. But overall, the relationship did follow closely. This was the first question that I was asked. It was asking if the upstream gate is set at a particular height and the downstream gate is removed, why the height stays at that upstream gate height the entire way along. Well, as we know, as the flow moves, it is not subject to change unless acted upon by something that forces the change. A hydraulic jump is one example. This requires water to change elevations in order to continue on its flow path. As you can see in this video right here, the water is forced to move downwards because of the sloping elevation of the terrain. So this water will never change height in the channel because it's never forced to do so. The next question that was asked to me was to calculate the manganese roughness coefficient using a different value for the normal height of the water. The height they want me to use is the value of the height of the water at the end of the S2 profile. The average value of Yn used was 0.01933, and the value they want me to use is 0.021. So, using the equation presented below the graph, I was able to calculate the value to change to 0.00811 from 0.0777. And this is due to the fact that we have all the variables in the equations except for the Yn, which they wanted me to change. The next question asked me to show how flat the S1 profile is when measured from the ground, and then to also show the total energy lost in the flow just before the downstream gate. As you can see in the table presented here, it is clear that the S1 profile for the water has a steeper slope when measured from the channel height versus the ground height. The dy dx values are just much larger than any of the values for the slope, and using a value of y equals 0.19 meters for the total energy lost just upstream of the downstream gate was calculated to be 7.93 times 10 to the negative 5th joules. The final question asked me how sensitive the S1 and S2 profiles are to changes in the manganese roughness coefficient and what sources of error might contribute to errors in the roughness coefficient. And then to modify the value of N, we calculated in our experiment by 10%, show how the S1 and S2 profiles change. From the experiment, I was able to find that the profile is very sensitive to change. So, for example, if I took N to be 0.077 and increased it by 10% to 0.008547, the value of the S goes from 0.000581 to 0.00703. And although this change is small, it's a roughly 20% increase. And as seen in the next charts, all the energy losses values increased. The values of dy dx also changed, but by insignificant amounts. For N, the main sources of error stem from the measured value of Q, which is the flow measured.